Welcome back everyone. In this lecture we will continue with working with the Young tableaus in order to define the irreducible representations of the symmetric group. So, first we need a technical proportion. So, let us actually explain that proportion in terms of an example, then I will state the proportion. So, first let us look at this following example. So, let us say I have two partitions of n, lambda, mu, let us name them. So, now given this lambda and mu, let us take two tableaus. So, let us call T lambda to be the tableau, lambda tableau associated with lambda, and then S mu to be the mu tableau. So, now let us actually assume that the entries in the same row of S mu, they are located in different columns of T lambda. So, here is the assumption. So, entries in the same row of S lambda, sorry, S mu, they are located in different columns of T lambda. Okay, let us say we have two tableaus satisfying this property. So, that means no two elements in the same row of S mu belong to the same column of T lambda. So, that is the assumption. So, let us work with some example, then it becomes clear. So, take this for example, this particular one. So, you have 8, 5, 4, 2, 7, 1, 3, 6. This is my T lambda and my S mu is given by 1, 2, 3, 4 and 5, 6, 7, 8. So, now note that if we take entries in the same row of S mu, for example, let us look at this row 1, 2, 3, 4. So, they are all located in different columns of T lambda. So, 1 is located here and then 2 is located here, 3 is located here and 4 is located here. That means they are not in the same columns, they are in the different columns. Similarly, you can see that the 5, 6, so they are also like located in different columns. Similarly, the 8, 7, 8, they are also located in the different columns. So, now what we are going to claim actually, so given such situation, okay, so we will be able to find another lambda tableau, call it U lambda. Okay, here is the claim. So, there exists lambda tableau U lambda such that the following happens. So, the jth column of T lambda and U lambda contain the same set of elements. They contain same set of elements for all j. So, when you read it each column in T lambda and U lambda, so they have same set of elements. So, that means they are just permuted among themselves. And the second condition is, if you look at the entries of the first I rows of S mu. So, look at the entries of the first I rows of S mu, and that should be same as, not same as, that should at least belong to the first I rows of U lambda. So, this should belong to the first I rows of u lambda, and this should be true for all I1 to m. Okay. So, here what we do, we have the convention that the lambda is given by lambda 1 etcetera lambda L, and then mu is given by mu 1 etcetera mu m. So, L is the length of lambda and m is the length of mu, and both lambda and mu, they are given as partition of n, and we have this lambda tableau T lambda and S mu satisfying this condition. And once you have this condition satisfied, then we will be able to find this u lambda, another lambda tableau satisfying these two conditions. That is the claim actually that we have made. So, now let us actually see like how this claim can be proved, and before proving that let us actually work with the example that I have mentioned and then see like how this naturally can be obtained. So, let us go back to our example. So, let me just rewrite that example. So, you have this T lambda which is given by 8, 5, 4, 2, 7, 1, 3, 6. And then you have this S mu which is given to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, now what we want to do? We want to obtain this u lambda, and note that the u lambda should be obtained from T lambda by permuting each column, and then we should make sure that the entries of the first I rows of S mu belong to the first I rows of u lambda. So, that is what we want to make sure. So, now what we can do as a step 1, so we can actually consider element appearing of the first row of S mu, identify that element in T lambda. Okay. So, let us look at the very first row of our S mu and choose an element there. Okay. Then identify that element here in T lambda. So, now what we do? So, since this is appearing in row 1 and we need to actually move that element in T lambda to row 1. So, the best way to do is look at that column where this 1 appears. So, this appears in this 1 appears in the first column, then you just switch that 1 with whatever element that appear in the that first element of that column. Okay. So, what we are doing? So, as a step 1, we are considering element appearing in the first row of S mu and identify them, identify the in T lambda. So, that is what we did, and what we want to do? We want to switch that element. Okay. So, this is the third thing, switch that element its column of the first row of T lambda. Okay. So, we identified this one and then we switch that with, you look at that column and then take the very first element in the first row of that column, switch it with that. So, then what we get? We just switch these two and then we get something like this. So, we get 1 here and then 5 remains here, 4, 2, 7 and then you get 8 here and then 3 here and then you get 6 here. Now, you do the same procedure for the next elements. So, if we go to 2, If it is already appearing here in the first row, then we just leave it. We do not need to do anything, because what we want to keep is the entries of the first I rows of S mu should belong to the first I rows of u lambda. So, if we start with something that is already there in the first row of T lambda. So, for example, this 4 is also appear here in here. So, we just leave it as it is, we do not just touch, we just leave it as it is. And if we choose an element, let us say this 3. So, this 3 is not appearing in the first row. So, then what we do, we identify the column in which that 3 appears in T lambda, and then switch that with the first row element in that column. So, that means this 5 and 3 should be switched. So, you obtain this resulting lambda tableau, that you call it as T1 lambda. So, the T1 lambda is obtained using the previous procedure, and then you can see that it is exactly given by the following tableau. So, what we did, we kept this 1 and 8, it was switched. So, this is becomes 1, this becomes 8, this 6 is unchanged, and again what we did, we switched this 5 and 3. So, it becomes 3 here and 5 here, and this 4, 2, 7 we kept it as it is. Okay. So, the original tableau T lambda is here. So, which is given by 8, 5, 4, 2, 7 and then 1, 3, 6, and then from that we obtain this tableau. So, which actually makes sure that the first row of S mu is same as the first row of T1 lambda. So, now we want to do the same procedure and then go to T2 lambda. So, in T2 lambda what we want to do, again we want to play the similar game, but we want to compare with S mu now. So, recall the S mu is given by 1, 2, 3, 4, 5, 6, 7, 8. So, now the first row is taken care. So, this part is taken care. Now, look at the row 2. So, the row 2 has the elements 5, 6 and identify them in the T1 lambda and then see where they are appearing. So, this is so if you look at 5, 6, look at 5, 5 is already in row 2. So, we do not need to do anything with that, we just keep it as it is, and look at this element 6, the 6 is appearing in the third row of T1 lambda. So, now to make sure that the entries of the first I rows of S mu belong to the first I rows of u lambda. So, what we need to do, we need to switch this 6 with something. So, what we do, we just identify this column where this 6 appears, this appears in the first column, then you switch that with this second row of that first column. Okay. So, then you will be getting the necessary tableau that actually satisfies the property that the first two rows of S mu entries stay as it is as first two rows of this T2 lambda. So, we keep this first row 1, 3, 4, 2, 7, we do not change, but the second row what we do, we switch this 8 and 6, we get 6 and 8 here, this 5 we keep it as it is. So, now if we read this T2 lambda and S mu, we can see that so every time we have actually interchanged elements in single column. So, the columns of T lambda and the columns of this resulted tableau, they do not change, that is the first condition. So, that was made sure that the jth columns of T lambda and U lambda contain same set of elements for each column. And now we also actually made sure of second hypothesis, that the entries of the first I rows of S mu belong to the first I rows of U lambda. So, you can see that the T 2 lambda satisfies both the properties. So, that way you can actually set U lambda to be T 2 lambda. So, now it is clear using induction that this can be always achieved, okay, and that requires a little bit of proof. Maybe I will leave it you to actually do that. So, this proposition says for any given tableaus T lambda and S mu satisfying the property that the entries in the same row of S mu, they are located in different columns of T lambda, then we will be able to obtain this U lambda satisfying these two properties, that the columns of T lambda and U lambda, they contain same set of elements, and the entries of the first I rows of S mu should belong to the first I rows of U lambda. Okay, so, maybe let me just state this as a proportion. So, lambda and mu are given to be partition of n, and let T lambda and S mu, they are the two tableaus, lambda tableau and mu tableau, such that it satisfies the condition that entries in the same row of S mu are located in different columns of T lambda. So, this is the condition. So, then we can find U lambda, which is the lambda tableau, such that the jth column of T lambda and U lambda have same entries for all j from 1 to L. So, we are having the convention that length of L is L and length of mu is M. And the second condition is the entries of the first I rows of S mu should belong to the first I rows of this U lambda, and this is true for all I. Okay. And this is just can be obtained by using induction, like the way I told. Indeed, what you can do, you can actually using induction on R, which is smaller than M, you can construct this TR lambda as before, such that the jth columns of T lambda and TR lambda contain the same elements for all j from 1 to L, and the entries of the first I rows of S mu belong to the first I rows of TR lambda for all I up to R. Then taking R to be M, you will be getting this U lambda, and this can be done using induction. I am going to just leave it to you. It is the same procedure that I explained you in the example. Okay. So, now once we have this proportion, then you can see that if such situation appears, then that actually puts stronger condition on the lambda and mu. So, in such case lambda must dominate mu. So, this is what we call it as dominance lemma. So, the dominance lemma, which actually states something about this tableaux. that we had before. So, you take lambda mu to be partition and this T lambda and S mu satisfying the earlier conditions. So, they are tableau of respective shapes lambda and mu, and you assume that the integers in the same row of S mu are located in different columns of S lambda. Okay. So, this is such that elements or the integers in the same row of S mu are located in different columns of T lambda. Okay. If this is what there, so then we can conclude that lambda indeed dominates mu, and this indeed follows immediately from the proportion, because we are able to get this u lambda satisfying these two property. Now, note that the columns of T lambda, that is not actually changing. Okay. That columns of T lambda and u lambda, they have the same entries, and now if we actually look at the number of elements that appear in the first I rows of u lambda. So, what it is going to be? So, if we take the number of elements in the first I rows of u lambda, so that is going to be exactly lambda 1 plus etcetera plus lambda I. So, now our second hypothesis says the entries of the first I rows of S mu belong to the first I rows of u lambda. So, that means all the elements that you have in the first I rows should be there. So, that means this number should be greater than or equal to the first I rows elements of this S mu, which is exactly mu 1 plus etcetera mu I, and this is true for all I greater than or equal to 1, and that says exactly that lambda is dominating mu. Okay. So, this is actually very crucial lemma, which is a technical lemma. It will be used later in order to prove irreducibility of this some representation that we are going to construct now. Okay. So, this actually kind of motivates us the following. Okay. So, we can see that the way in which like we are viewing this partitions as these Venn diagrams, so that gives lots of advantages. So, when the Venn diagrams actually in a way motivated from understanding the partitions of N, which are the indexing set of the conjugacy classes of the symmetric group. So, now so let us actually construct the irreducible representation. So, here is the construction. So, once we construct, again we also have a job to prove that they are indeed irreducible, but for that let us fix some notations. So, suppose if we take a subset 1 to n, so then we identify this S x to be all permutation that fixes elements outside of x. Okay, this is those permutations of S n which fixes I for all I which are not in x. Okay, so that is what we call it as S x. And now, given any Young tableau, we can actually define what is called column stabilizer of the tableau and row stabilizer of the tableau. So, let us fix the notation. Let us call this T. So, this is a Young tableau. So, now the column stabilizer of this T, which is denoted by C t, this is those sigma in S n such that it actually just leaves each column invariant. So, that means this is there in CT if and only if I is in some column, then sigma I also should be in the same column. So, sigma of I is in the same column as I, and this should be true for each I in 1 to n. Okay. So, this is what called as column stabilizer of T. So, this is column stabilizer of T. And similarly, one can also define what is called row stabilizer, which is denoted by RT, which is by definition you take all possible permutations of Sn such that again sigma I is in now the same row as I for each I 1 to n. Okay. So, this is what you call row stabilizer of T. Now, let us look at one example. So, take the tableau to be the following. So, you take this 1 3 7 and then let us say 4 5 and then 2 6. So, now if you look at this CT, so then the stabilizer of this is going to be, so if you look at this column, it should permute among themselves this. So, that means the rest of the elements should be fixed. So, this is exactly S of 1 4 2, and then since all these columns are different. So, the stabilizer will be just the product of elements that stabilizes each column. So, this is going to be exactly the product S 1 4 2 and then 3 5 6 and then S singleton 7. Now, it is clear that the cardinality of this CT is going to be just the product of the cardinality of this each group, and so the permutations of 1 4 2 is just a permutation on 3 letters. So, this is going to be 3 factorial times 3 factorial times 1 factorial, which is the cardinality of this column stabilizer of this CT, and which is true for any tableau. Like if you take lambda, which is partition of n, and then look at the tableau T. So, let us say this looks something like this. So, some entries are there A11, AK11 and so on, A12. So, now if you look at this, so the column length, let us say the column length is given by C1, C2 etc. some CP. So, then the stabilizer CT, so this is going to be exactly equal to C1 factorial times C2 factorial etc. CP factorial. So, this is going to be the number of elements in the column stabilizer of CT, and the corresponding group CT will be the product of the symmetric groups that permutes these individual columns. Okay, that is easy to see. And note that the symmetric group acts on this set of lambda tableaus, and the way it acts. So, if you take a tableau T and then given sigma in Sn, what you do, you look at this sigma T. So, you just apply sigma entry wise in each box whatever filling that it has. Okay. So, for example, if you have something like this 1 3 4 2. So, this is my T, and then let us take sigma to be 1 3 2. Then what is sigma T? So, we are going to just apply sigma on each element, sigma 1, sigma 3 and sigma 4, sigma 2, and we can easily see that sigma 1 is 3, sigma 3 is 2 and then sigma 4 is 4 and sigma 2 is 1. Okay, so that is going to be my sigma t. So you just apply sigma to each entries of t, then you get sigma t. And it's not very difficult to see this action is indeed a transitive action. Okay, so Sn acts on the set of lambda tableaus transitively. Okay, I will leave this as exercise. This is not actually very hard to prove. So now what we have, so given tableau, so we have the columns and we have the rows. So now we have to actually fix one of them and then use this symmetrizer to get the elements that we are interested in. So for that purpose we need to define what is called a tabloid and then polytabloid. Okay, all those terminologies maybe I will define in order to like define the irreducible representations. So first what we do, we actually construct this very big representation called this m lambda, so which will be spanned by tabloids. Okay, so this is the span of tabloids. Okay, and then inside this we define what is called this polytabloids. Okay, inside this we will have this what is called this S lambda, so which is the span of polytabloids, and this is going to give us the irreducible representations of the symmetric group Sn. Okay, so for that we have to start with the definition of tabloids, and yeah, since we have to fix either rows or columns, what we do, we actually first fix the rows and then define equivalence class with respect to the rows. So we call two tableaus, they are equivalent if for each row they have same set of elements. Okay, you call this T lambda and then S lambda. Okay, you have taken two lambda tableaus and then you define they are equivalent if they have same entries in each row. Okay, and the set of equivalence classes, and that will be the set of tabloids for us. So an equivalence class of lambda tableau is called a lambda tabloid or tabloid of shape lambda, and what we will be interested in, we will be interested in the set of tabloids. Okay, so for example what we are telling, so let us take this 1 2 3 4 5 and this is equivalent to, so I can just permute among the rows. So for example I can take just 3 1 2 and then keep this 4 5 which is equivalent to 3 1 2. I can also permute this 5 4. Okay, all these are equivalent. So now we just call the equivalence class as tabloid. So yeah, tilde equivalence class of lambda tableau is called a lambda tabloid. And we have this notation T power lambda. So this we denoted by the set of all possible tabloids of shape lambda. Okay, we fix the shape lambda and we collect all possible tabloids of shape lambda, and that we denoted by t power lambda. And we also have this unique tabloid which is associated with this following element. We denote this t lambda, sorry, t lower lambda. So, this is the equivalence class associated with the following tableau. You fill this 1 2 lambda 1 in the first row, and then you fill lambda 1 plus 1 etc., lambda 1 plus lambda 2 in the second row, and so on. At the end it will be lambda 1 plus etc. plus lambda L, which is exactly L, and it will end with lambda 1 plus etc. plus lambda L minus 1 plus 1. And you take this unique tableau, and then the tabloid associated with that is denoted by T lambda, and this notation again will be used later. And we will prove that there is a natural action of the symmetric group on the set of tabloids, and that will make this the C span of these tabloids to be a symmetric group representation, and that representation is going to play an important role in order to construct the irreducible representations. Okay, I will stop here. I will do the construction in detail in the next class. Thank you.